Okay, so let me do this question. It looks like I've done this question before, but as a part of the pre-lab preparation, and it's also homework question, and the focus is slightly different when it's a pre-lab question versus when it's a homework question. So let me right now do this as a homework question, and I'll later see which version I want to use for the homework help video on that page of homework help videos. So this question says the figure below shows bullet of some mass. Let me just start doodling and just writing down symbols so that I understand what information is given to me. Bullet of some mass traveling horizontally toward the east with a speed, let me say V naught for initial, which strikes a block of mass, let's say capital M. That applies both the description up there and the figure here. That is initially at rest on a frictionless table. Okay, seems simple enough. Moving at some speed V naught. After striking the block, the bullet is embedded in the block. So for the kind of post-collision picture, what we have imagined is you have the block and you have the bullet that's been embedded, and I think they're going to be moving together at some speed V final. So I have that picture in mind. Embedded, move together as one unit. What is the speed of the bullet block/bullet combination immediately after the impact? So hint will probably ask you to consider the conserved quantities. So we are deep into conservation law strategies. And when you are applying conservation law, so we don't have kind of fixed set of steps that I've given you like with the standard strategy, but this is what I might recommend. As a kind of first or maybe even 0th step, you should identify the conserved quantity. And at this point in the semester, it's super easy. You basically have two choices. You could be conserving energy, or you could be conserving momentum. And later on the semester, you could potentially be conserving angular momentum. But right now, energy or momentum. And in the lecture, you've been told the conditions that's necessary for conservation of energy and momentum. For energy, the condition you need is no net work by non-conservative force. And for momentum, the condition you need is no impulse due to external force, or I guess net external force. Now, having said all this, there's one other thing you have to be careful when it comes to energy conservation. Sometimes the problem won't explicitly tell you you have these non-conservative forces. So you need to kind of figure it out from reading the question. And for this question, the biggest hint is where it says the bullet is embedded in the block. And what that means is this is what we describe as a sticking collision. And in sticking collision, energy is not conserved. It's an inelastic collision. In fact, it's what we call completely inelastic collision in the sense that it loses as much kinetic energy as possible. So if you remind yourself through all this, then what you should realize is, so in this question, only momentum is conserved, assuming no net external force. And looking at this, especially because they told us frictionless table, there is external force, gravity and normal force, but they balance each other out, so no net external force. And I will tell you, even if the table hadn't been frictionless, a lot of times we would come up with an argument why friction can be neglected. Maybe the impulse due to friction is negligible compared to the impulse due to the interacting forces. So we've identified the conserved quantity, momentum. Then the first and maybe the only step is you write down the conservation law statement. So state the conservation law. By which I mean, you say your initial momentum, the total initial momentum, is equal to total final momentum. And the rest, hopefully, you remember the definition of momentum, and you can write those down in terms of the quantities that are in the problem. So let's do that. So the definition of momentum is mass times velocity. So for initial picture here, or snapshot 1, before the collision, you have momentum of the bullet, mass times v naught, plus the momentum of the block, which will be 0, but let me just write it out for clarity. Big mass times 0 for the velocity of the block. That should be equal to the final momentum, final total momentum, which, let me say the total mass of this combined object is the small m plus big M, treated as just one object. Small m plus big M, which is moving at speed of v final. So this is one equation in terms of one unknown v final, which is what we are looking for. So let me do that algebra in my head and write it down here. V final is equal to small m divided by the sum of the masses times v naught. If you want to double check my algebra, pause the video, do it for yourself and make sure I didn't make a mistake. And I'll plug in all the numbers all at the end and just type it in into the homework system to make sure I didn't make a mistake. Okay, part B. What is the magnitude and direction of the impulse by the block on the bullet? Oh, okay. So let me just doodle a little bit to make sure that I understand. So we are thinking of the kind of what's happening in the process of the collision. So bullet is trying to getting embedded. So I can draw free body diagrams for this bullet and the block. The free body diagrams would look like the bullet, it's slowing down, so there must be an applied force this way. The block is speeding up to the right, so there must be applied force that way. And this should be action-reaction forces. There are internal forces, and of course, there are other forces like gravity and normal force. But I'm just ignoring all those because they balance each other out and they don't affect anything. So the direction of impulse by the block on the bullet, that's describing this. So here it must be leftward. Then the block exerts an impulse. Oh, for the impulse, you have to know the definition of impulse. Impulse, sometimes indicated with the letter J. I just never got used to it, so I'm just going to spell it out. Impulse can be written two different ways. It can be written as, this is the definition of impulse, force times the duration of time. Now here, this won't help you because you don't know force, you don't know duration of time. So the other description of impulse that's helpful here is the impulse as the change of momentum. So here you can figure out the change of momentum of the bullet. So the change of momentum of bullet of mass m is going to be its final momentum minus its initial momentum, which is its final speed. Let me write out the answer we had from A. Let me just keep it as a symbol. So because as I plug in the numbers, I'll have a numerical value. I'll just remind myself to use that. So it'll be mass of the bullet times its final speed, whose numerical value we know from part A, minus speed of mass of the bullet times its initial speed v naught. So doing simple simplification, the expression for the impulse on the bullet is the absolute value, vector out the mass, times the v final minus v initial. I'm putting the absolute value because I think if you put in a negative number here, which I think my final number here will be, system will say this answer is wrong because you already indicate the direction here. It's not expecting you to double indicate the direction. Okay, the magnitude and direction of the impulse from the bullet on the block. Now, I could go through this calculation again if I want to. I actually don't have to. If I believe in the conservation of momentum, which comes from Newton's third law, I know the answer here is the same as B above. So I don't have to redo this calculation using the mass of the block. Don't need to. I trust in Newton's third law. I trust in conservation of momentum. So I'm just going to use the same answer as B. Now the direction will be rightward, again, because I trust in the Newton's third law when the conditions are met. So I'll simplify the calculation, just use the same number for C. Part D, if we took 3 milliseconds for the bullet to change the speed from the initial speed, yeah, it's just stating it twice, not a different number, to the final speed after impact, what is the average force between the bullet and the block during this time? So this is where actually this relationship is helpful. So we already figured out the impulse. So using the thing on the far right. So all we have to do is just solve for force, and we are done. We are now given delta t. So let me solve that for force. The force is change of momentum, or the impulse, divided by change of time. Yeah, and I guess since we will have the change of impulse from parts B and C, let me just write it that way. The magnitude of the average force is the absolute value. The change of momentum from B and C above, divided by the duration of time that the question here gave us. And I'll make sure I put in a positive value because the question is asking for magnitude. Okay, of the kinetic energy initially present in the bullet, what percentage still remains as a kinetic energy of the block/bullet? Oh, okay. I think I just have to do the calculation. So I'll break up the calculation this way. I can say the final kinetic energy is going to be 1/2 the total mass, the sum of the masses times the V final squared, and the initial kinetic energy is equal to 1/2 the small mass of the bullet times its initial speed squared, and for this percent remains as kinetic energy 100 times K E final divided by K E initial. Yeah, and I'll get a numerical answer and plug that in. So yeah, let's get all the numbers. I'm gonna just use regular calculator here because I think switching between Wolfram Alpha and this screen, I can anticipate them being super annoying. So let me just use regular calculator. I'll just keep everything in basic SI units. I'll do some conversion as we go. So the masses, I'm gonna convert 70 grams to kilograms, so 0.07 kilogram. So 0.07 kilogram divided by sum of that with 4.5. I can do that in my head. So 4.57 kilogram, that's the ratio of masses, times 300 meters per second. I'm gonna keep an extra significant figure because I will be using this number in later parts. So I'll write down 4.595 meter per second. 4.595 meter per second. For the grading system, all that's required is only the 3 significant figures, but I want to be extra sure that rounding error doesn't affect my answers later. So the magnitude and direction of the impulse by the block on the bullet should be the mass, 0.07 kilogram times the parenthesis open, 4.595 minus 300, parenthesis close, is equal to minus 20.68, or absolute value, so 20.68. 20.68, and because I kept everything in basic SI units, I'm guaranteed that this answer should be in basic SI units. And it'll be the same answer for part C, nothing's changing. I already indicated the directions. So for part D, so I have this, I'll just leave it as minus and just remember not to write it down. I have this impulse from parts B and C. I just need to divide by the time. So I need to divide this by not 3, but 0.003 second. That's the 3 milliseconds. So 0.003 second or 3 millisecond. And that should be, pretty large force. 6,800 and Newton. 6,890 Newton. I'm keeping only three significant figures because this is not gonna be an intermediate number anywhere. So, all right, that's D. For E, so I need to calculate the kinetic energy first, and then I'll do the rest. So, for kinetic energy, the final kinetic energy is 0.5 times the sum of the masses. Oh, I think I remember 0.457, I think. Is it? Yeah, 0.457. 0.457 times the final speed. I have that here, 4.595. 4.595 squared is equal to, this should be in joules, 4.825 joules. And I'm keeping 4 instead of 3 significant figures again because this is an intermediate number. I want to be extra sure rounding error doesn't affect my final answer. So for the initial kinetic energy, it should be 0.5 times the mass, which is 0.07 kilogram, times the initial speed squared, 300 squared. So 3,150 joules. 3,150 joules. Let me double check. Now, it shouldn't surprise you that initial kinetic energy is bigger than the final kinetic energy because, in inelastic collision, you lose energy. It might surprise you just how big the discrepancy are, but I think it makes sense. If that block had been of an infinite mass, it would have lost 100% of energy and would have had a 0% of energy remaining. Now, the mass isn't infinitely large. It's only I don't know, a little less than 100 times as large as the bullet. So I think this amount of energy loss makes sense. So let me calculate the percent of energy remaining. That should be 4.825 divided by 3,150. Very small number multiplied by 100 for percent, 0.153%. I think that's right, 0.153%. Okay, let's just plug in the numbers. Make sure I didn't make any mistake, or if I did, fix it. All right, so let me just copy over those numbers. 4.595, 20.68, leftward. Oh, it's not an option. Did he talk about east is right and west is left? So I'll say westward. And then same number, this time eastward. So the force here is 6890. Kinetic energy 0.153%. And not a typo. Let's hope that everything is correct. I missed something. What did I miss? I don't know. Did I make a mistake? I mean, the expressions are right. Let me do this on Wolfram alpha in case I made a typo, maybe. It's always possible. I could have made a mistake on the calculator. So let's say 0.5 times 0.07 plus 4.5 times speed, which 4.595 squared. Oh, I definitely did make a mistake because that's 48.25, not 4.825. Okay, that means I think I made a factor of 10 error. Yeah, not sure how that happened, but let's fix that factor of 10 error, and let's hope it's graded as correct. Yeah, I don't understand where in the calculator I made a factor of 10 error, but it ultimately doesn't actually matter. So, and I don't have calculator history to go back and make it. So let me just fix it here. So, not here. Start here. So yeah, that's this question. If it's got a lot of parts, and it asks you to understand all the connections between impulse and the force, and it's not that difficult of a question. It's just long, and it um, requires you to remember all the definitions relating to sticking collisions.